For the last 2 years, the artificial intelligence industry has been defined by one metric: speed above all else. Generating instant responses is effective for basic queries, but that millisecond latency inherently limits the depth of the reasoning process. Sakana AI's Marlin is a departure from this focus. It is a system engineered for deep research and long-horizon tasks that require hours of computation. This comparison shows the difference in intent. While standard models provide a few paragraphs in seconds, Marlin works for 8 hours to deliver a 100-page, consulting-grade report. Marlin is an autonomous virtual chief strategy officer. It is designed to work independently over a full workday, formulating its own hypotheses and verifying its own data. For enterprise-level strategy, the race for speed has reached a point of diminishing returns. Complex global problems require a system built for depth. Sakana AI was built in Tokyo, a deliberate choice to escape the investment bubbles and the faster-is-better culture of Silicon Valley. Co-founder Lion Jones was one of the original authors of the paper that introduced the transformer architecture, which serves as the foundation for modern models like GPT and Claude. Jones eventually left Google, arguing that the industry's fixation on scaling single monolithic models has calcified creativity and blinded researchers to more efficient architectures. He joined David Ha, a pioneer in nature-inspired computing, who believes the solution to complex AI problems lies in learning from biological systems. The fish metaphor illustrates how complex intelligence can emerge from a school of small, specialized models working in coordination. By applying this decentralized approach, Sakana AI is attempting to bypass the computational limits of building a single trillion-parameter model. Standard language models use a method of repeated sampling, generating text in a linear pass, with no ability to pause and rethink their conclusions. Marlin utilizes inference time compute scaling. This shifts the heavy lifting from the initial training phase to the actual moment the system solves a problem. To manage this computation time, Marlin uses an engine from chess supercomputers, Monte Carlo Tree Search. It maps this logic onto corporate research, substituting board moves for distinct hypotheses, mathematically evaluating their potential success before drafting any text. This scaling ensures the system evaluates thousands of logical paths before committing a single word. The engine uses a technique called adaptive branching to dynamically decide when to pivot and when to focus its research. Encountering a contradiction or lack of verifiable data, the system recognizes a dead end. This triggers exploration mode, spawning new lateral hypotheses. Identifying promising angles shifts it to exploitation mode, driving vertically to gather primary sources and deepen analysis. This 8-hour loop of exploring lateral ideas and exploiting deep data allows Marlin to self-correct its own errors without human intervention. This raises a crucial question of system orchestration. What specific mechanism is actually executing these thousands of simulated research branches? Marlin operates through multi-LLM orchestration, managed by a central coordinator node. Acting as a conductor, it selects the best specialized model for every subtask, routing creative hypothesis generation to an ideation model and rigid fact-checking to a logical verification model. These underlying models, like GPT-5 or Claude, can be swapped dynamically based on the specific microtask. Enterprise-grade intelligence is achieved by orchestrating a team of elite specialists to act as one unified brain. During its closed beta, Marlin was used to analyze complex geopolitical scenarios, such as the economic impact of a blockade in the Strait of Hormuz. For corporate use, Sakana employs a closed-loop data policy, ensuring no customer data is used for training and all personally identifiable information is removed. The result of this 8-hour cycle is a fully audited 100-page report that matches the comprehensiveness of a human research team. This creates a specific division of labor. Marlin functions like a junior consultant, automating the weeks of data gathering and synthesis that precede a final human-led decision. The traditional approach of building massive, monolithic AI models now faces a direct threat from decentralized, highly coordinated networks. The arrival of Marlin suggests that progress in AI is becoming less about the scale of a single model and more about the orchestration of specialized systems that think over time.